So it's not too different than what we did last unit in that we're going to have, we're going to say that our net force equals MA. That's what we did last unit. Although what we're going to do in this case is we're going to say that since it's a centripetal force, I'm going to call it FC and AC. And in this case, the centripetal force is equal to what minus what? What do we think?
Force newtons minus force gravity.
Yeah, normal minus gravity. Yep. Equals M. And then remember, we have the equation for AC from our notes from last time. So it's V squared over R. So I'm going to say Fn minus Fg is equal to mv squared over R. And then in this case, I'll just say we know that gravity is mg. And that's just an equation we can solve. Let's see here. So I end up getting 11,955 newtons. Any questions about that? So what I'm doing is I'm just combining what we did last time with this side of the equation is just what we were doing last unit. Why is M also over R? Good question. So if I say 3 times 1/4, that's the same thing as saying 3/4, right? So if that's the case, if I say M times V squared over R, that's the same as saying MV squared over R, because you can multiply numerators. Does that make sense, Russell? It's more just so I could, yeah, if you wanted to do 600 times quantity 9 squared over 8, yeah, that would work. Why 9.8 G? G is 9.8 because this is force of gravity, so mg is 9.8. Trey, Eros, what happened to the other side of the equation? Okay, so let me clear this up because it's a little bit confusing what I did here. Right, so here I got MAC. AC from last time is V squared over R. So this becomes M times V squared over R, right? And then this is what I was showing to Russell when he asked, right? M times V squared over R is the same as MV squared over R. Does that answer your question, Eros? All right. Any other questions about this? Maya asked me to let you know. Got it. Thanks. I'll take a look at it after we're done. Thanks, Kenzie. All right. So there's that. Now let's look at part B. Is going to ask, okay, what changes if now I'm at the top of the track? So what I want to do, I'm going to redraw a picture here, but now we're still going to be going 8 meters per second, but we're going to be doing it at the top of the track now. So now I'm going this way. I'm at the top. Now, let's think about what our forces are now. Well, we still are the same car, so we probably still have the same weight. We're still going to have the same force of gravity. However, which way does the normal force point this time? So a normal force is a surface, so we're used to a normal force pointing up. But if you think about this, this is kind of why I showed you the hoop, right? if I'm, I know that this is not going up, but if I'm at the top of the hoop here, right? What's happening here is the hoop is preventing me from going up, right? So the same thing here with the track. The track is actually preventing the car from going up. So we're going to have a goofy situation here where the normal force is actually pushing us down. And then I'm going to draw the centripetal forces being that sum, right? So when I do this, again, this side is going to become mv squared over r. This side, though, is now going to become gravity plus normal because they're pointing in the same direction. So I've got mg plus normal force equals mv squared over r. So I missed the net force on the last one. What do you mean, Russell? Where it pointed? Oh, fair enough. So the centripetal force always has to point to the center of the circle. So if I'm at the bottom, the center is above me, right? So that's why this net force points up. If I'm at the top, the center is below me, right? So it's got to point down, right? So this isn't really to scale, but it's kind of like here. Wherever I'm at, I guess I should really call these the net centripetal force. Wherever I'm at, the net centripetal force needs to point to wherever the center is. All right, so if I do this, I think I come out with 195. Questions there? I just want to look at these two parts side by side for a second because it's a little strange how much the normal force changes. Could the masses cancel out? I'm glad you asked that question. Can you show math just for reference later? Yeah, okay. All right, so give me a second. Let me take these one at a time. Russell, could you cancel out the masses? No, because there is not a mass in every term, right? If it were just these two terms, I could, but since that term does not have a mass in it, you cannot cancel all the masses. So no. Can you show math just for reference later? You mean you want me to like actually solve this out, Trey? Is that what you mean? You want to see it expanded? All right, cool. Yeah, we'll do that, and then I'll get to Aiden's question because Aiden's question is really interesting. So if I go, so 600 times 9.8 is 5880 plus Fn equals 600 times 81 over 8. So that's what I get. Subtract 5880 on both sides, and you get a normal force of that. So Aiden's question, why are they so different? So this is what's really interesting, and you got to think about what the normal force is doing, right? So remember, a normal force rises to meet whatever is asked of it, right? So if I'm sitting on a ground, the normal force sort of rises to meet whatever weight I put on the ground. Well, in this case, that's not what is being asked of it, right? In order to go in a circle, the normal force is pushing you towards the center. That's what it's trying to do. When I'm here at the bottom, the normal force has to do two things. It's got to cancel out all of the gravity and push me towards the center. But when I'm up here, right, the gravity is helping me get to a centripetal force. So normal force does not have to cancel out gravity. As a matter of fact, gravity is helping out the normal force. The normal force just has to provide what's left over as far as the centripetal force that's needed, right? So here, the normal force is doing double duty. It's canceling out gravity and pushing us towards the center. Here, it's only doing half duty because it's just gravity's already started pulling it towards the center. The normal force is just doing whatever else is needed to get it to the center, right? So you can actually kind of imagine this. Well, so what would happen if there was no gravity? Okay, that's a good question. So if there was no gravity, that's essentially what I was doing here, right? This is a loop with no gravity because gravity is going a way that doesn't matter. So there would just be a normal force, and the normal force would be the entire centripetal force. I'm assuming that the normal force at the bottom will always be greater than the normal force on the top. In a loop, yes. Now, we're going to do a problem in a second where it's like a hill, right? So if you're going around this side, right, if you're going around a hill, in this case, normal force is going up. So it's a different situation. But yes, Landon, in any case where I'm in a loop-to-loop, it's going to be bigger at the bottom and smaller at the top. All right, any other questions about this? Okay, to fill this out, and I think that I started to say this, but I think that this might help us think about Aiden's question a little further. Let's imagine that I just want to know the minimum speed that the roller coaster could have at the top and still be in contact with the track. Okay, so let's draw this out and then we'll talk about what this means. So now we're going to say it's not going 9 meters per second anymore. We're just trying to figure out the minimum that it can go and still make it around here. So I'm up here. I want to say, what's the minimum velocity? I still have a mass of 600 kilograms. So let's think about this, right? Remember we said that in order to go in a circle, you need both things. You need to have forward motion and you need to have centripetal force, and they have to be balanced, right? If you have too much centripetal force, going back to this drawing, right? If I have too much centripetal force, the result is going to be that I go towards the center. Now, here's what's happening in this case, right? No matter what, when I'm at the top, there is one force that I can't do anything about. There's one force that's always there. And that force is gravity. What's happening here, right, is if as I get slower and slower, if you look back at this picture, as I get slower and slower, you need less centripetal force. Less centripetal force means that my normal force can shrink and shrink and shrink until my normal force gets to 0 at the minimum velocity, right? So in this case, we're going to say that the normal force is 0. If I go any slower than this, what's going to happen? If I go any slower than this, I'm going to have more gravity than I need. So I'm going to have more things pulling me towards the center than I am going to have forward motion. And so what am I going to do? I'm just going to fall off, right? So this would be, if I want to stay in contact with the track, I have to have my normal force equal to gravity. If I go any slower, I don't have enough forward motion to sustain that centripetal force, and I just fall off, right? So what we're going to say here is, in this case, the centripetal force is equal, well, it's always equal to MAC, but in this case, the centripetal force is also equal to gravity. M B squared over R. Are we assuming that? Correct, Russell. So yeah, so in reality, you've got the coaster is actually attached to the track in another way. But yeah, correct. But a well-designed roller coaster never uses those. So that's actually a good point. So yes, real roller coasters are going to be somehow attached to the track, or there's going to be wheels under the track so that it's staying gripped to it. But if it's a well-designed roller coaster, you're never using those safety wheels because you've got enough speed that you don't need to. Fair enough. So yes, force of gravity is mg. And to Russell's earlier point, in this case, I do get to cancel out masses because there's a mass on both sides. And every term has a mass in it. So what, we got 9.8 equals v squared over, what was the radius again? 8 meters. So it actually sounds like this roller coaster was playing with fire a little bit because it was only going 9 meters per second, which was not too much faster than it needed to be going at minimum. So. All right. So the key is if I have a minimum speed when we have a loop problem like this, or there'll be a one on the practice in a second where you've got a ball on a string and it's asking you minimum speed. But in that case, right, the idea is you can, if you're going vertically at the top, you can never get rid of gravity. So your centripetal force has to be at least equal to gravity. If you go any slower than that, then you are going to fall off the loop, or you're going to kind of like cause slack in the string or whatever the situation is. Yeah, so that's a good point, Eros. To talk about the normal force, it would probably make more sense to be talking about a car or a motorcycle where there wasn't those safety, those other safety issues. All right, here's what I'd like to do. So I have in today's folder, there is a day 37 assignment. There are 2 problems here. Also, the answers are there for you to check. Just like we did before, you just stay on Zoom. That way you can answer questions as they come up. And then when you turn it in, you'll be done. All right, 2 questions. Why is a normal force 0? So, so again, everyone, you guys can go ahead and start on this. I'll go ahead and answer these questions while you guys are starting. Let me go back to my picture, Shrey. So why is the normal force 0? As I slow down, imagine this picture, right? As I slow down, because the centripetal force is equal to mv squared over r, as the v gets smaller and smaller, the centripetal force gets smaller and smaller. There's nothing I can do to change my gravity. So the only thing that can do to make the centripetal force get smaller and smaller is for the normal force to get smaller and smaller and smaller. It keeps getting smaller until it gets to 0. Then it can't get any smaller than that, right? Does that make sense, Shrey? Does that answer it, right? Where we're kind of trying to get the centripetal force as low as possible. And the way to make the centripetal force as low as possible is for the normal force to be 0. Yes, correct. Because the faster you go, the more force you need. The slower you go, the less centripetal force you need. Because of this equation. Landon, is there a maximum speed that you can go on a loop? The maximum speed would just be dictated by how strong your surface was, right? So you could imagine, for example, like, you could imagine a situation where you might break the track or whatever it is. But in principle, the only thing you're limited by is by however much normal force the track can give you, which is just basically how strong the track is. So in principle, no, there's no maximum speed unless you get to the engineering constraints of the actual metal. And that I suppose that is also true. That yes, that there is a speed limit in the universe. It is impossible to go faster than the speed of light. I would imagine that our loop would fail before we got to the speed of light, though. Eros, there's a video posted there. Oh, you just want to see what I was showing? I can put this up for a second. But there's a video posted in last time's folder that it would be a good idea to take a look at, because there were also some practice problems we did last class.